Hi everyone, this is Mike back with another Calculus in a Nutshell video, this time to talk a little bit about integration, which you will be studying in modules 5 and 6. This is like the other Nutshell videos, an introduction potentially if you're watching this at the beginning of module 5, or you could consider it a way to think about wrapping up Module 5, so you could be watching this at the end, and my hope is in either case it will be helpful to you. So let's remember where we are. Calculus is about 3 primary topics. You've studied limits back at the beginning of the course. We've spent a long time talking about derivatives in modules 3 and 4. Now here we are in module 5 discussing a new topic called integrals. It's important to keep in mind that both derivatives and integrals are closely related to limits. In fact, both of them are defined as limits. And so, as I've mentioned multiple times, this entire course really is about one idea, which is limits. But derivatives and integrals are important enough that they get their own attention. So we're nearing the end of the course, but still not quite finished. There's a lot to talk about with integrals. So let's just go over a few basic and important things about integrals. So just like derivatives, you can think about those, or one shorthand way to think about integrals is to think about, one shorthand way to think about derivatives is to think about slopes of tangent lines to curves. A shorthand way to think about integrals is that they are areas under curves, or maybe more precisely areas between a curve and the x-axis. So we have lots of formulas for area, for polygons and other regular shapes like circles, or even three-dimensional shapes like cylinders or rectangular prisms. But what about more irregular shapes or figures bounded by unusual curves? So that's one big thing that integrals can do for us. They can help us find areas to strange shapes. Well, we can estimate area using easy, small approximations in the same way that we estimated the slope of a tangent line using the old definition of a slope of a secant line between 2 points. So we can estimate area just using a collection of rectangles. And finding the area of a rectangle is easy. So we just use a collection of rectangles and we add up all of those rectangles together to get an approximate area. And then if we take a special kind of limit, then those rectangles will help us find an exact value for the area between a curve and the x-axis. It's also important to remember that integrals are signed areas. So what that means is that areas in this context can be considered negative. That's often found when you are looking at areas underneath the x-axis, so between the x-axis and a curve that's below the x-axis, or in some cases if you are moving in a direction from right to left. Typically in the coordinate plane we move from left to right, but if you move in the opposite direction, that can also produce negative areas. The idea here, just like with motion and derivatives, depending on the direction you're moving, the quantities that we're talking about often have a direction assigned to them, and so the integrals also have signs that are meaningful. It's not typical that we talk about areas as being negative, but in this context they can be, and it's important to keep that in mind. And just a quick caveat. So just like derivatives are so much more than the slope of a tangent line to a curve, integrals are actually more than just being an area under a curve. But it's also the basis on which a lot of the other ideas are founded. And so it's an important way, important shorthand, I guess you could say, to understand what integrals tend to mean. So just a look inside Module 5. So the first section in Module 5 is just an introduction to integrals. It talks a little bit about where integrals come from and what they mean and some basic rules about how to work with them. Then in section 5.2, there's a formal definition of integration that takes kind of the intuitive idea that's brought to you in section 5.1 and makes it a little bit more formal. It shows where the limit definition comes from, and there's a lot of technical aspects in section 5.2. I would encourage you strongly to pay attention to those because that's really the foundation on which the idea of integration is based. And then section 5.3 seems to take a detour into something called antiderivatives, and antiderivatives are what they sound like. They are the opposite of taking the derivative. So whatever you do to take the derivative, if you do that in reverse, that's an antiderivative. And so that feels a bit like a detour because in sections 1 and 2, we're talking about integrals and finding areas and limits of rectangle areas, things like that. And then in section 5.3, there's this business about antiderivatives and going backward from all the differentiating you've been doing. And it seems like a detour, but some of you already know how this plays out. You know what the spoiler is at the end, and that's actually what section 5.4 is about, something called the fundamental theorem of calculus. And it turns out that when you do the opposite operation of differentiation, when you take an antiderivative, that actually is finding an integral. So strangely enough, doing a derivative backward actually helps you find the area under a curve. And if you think about it, and there are some videos in the lessons that describe how this works, it actually makes some sense why a rate of change, why if you did the opposite operation on a rate of change, you would get something called a total change or an area under a curve. But the fundamental theorem of calculus actually links these two ideas together, derivatives and integrals, and that's a really important section to pay attention to. Section 5.5 is about the net change theorem and indefinite integrals. So there are actually two different kinds of integrals that you'll study in Module 5, and section 5.5 talks about the second piece of that. And then there's one kind of special technique about integration in section 5.6 that you'll learn about called U substitution. And that's essentially the chain rule for integration. It's a little bit more complicated than the chain rule in some ways, but in other ways it's really just the chain rule in reverse, just like, as I mentioned, antiderivatives turn out to be integrals from the fundamental theorem. So that's a look at what you'll be studying in, or maybe what you have already studied in Module 5, and hopefully those things either will soon come to make some sense and coalesce together into a themed set of ideas, or if you've already studied them, you get a sense about how those things, you have a sense of how those things are fitting together. Now, just a few quick tips about integration. So remember the connection to areas. That's something important to keep in mind, just like I suggested keeping the idea of slopes for derivatives can be helpful. If you keep in mind that derivatives are just rates of change, that can take you a fair way in terms of understanding the other things surrounding the ideas of derivatives. And the same is true if you try to keep in mind the connection to areas when it comes to integration. As I mentioned, differentiation and integration are closely related, and so if you are highly skilled at differentiation that we've been studying over the last few weeks, then integration will become easier. Now, having said that, it's important that you not think too closely about the connection between differentiation and integration, because a lot of times the mistake that people make is thinking that in every way, shape, and form, integration just mirrors the process of differentiation. And that's true in theory, but in practice, some of the formulas that people use for differentiation are not as easy to unwind as it might seem. And it turns out that integration, in terms of a symbolic process, and a lot of the shortcuts and formulas that you use for differentiation turn out to be more complicated in integration. And so, in fact, Calculus 2, a big chunk of Calculus 2 is about learning some of those special rules for integration that were a lot easier to learn for differentiation. So it's important not to get the rules confused. They tend to be more complicated for integration than for differentiation. One other thing is to recall the meaning of differentials. So they represent extremely small incremental changes in a variable. So you've already worked with dy and dx in terms of derivatives. Those quantities, dy and dx, are also going to show up in integrals, and they refer to the same basic idea, but it's important to keep in mind what they mean. They represent extremely small incremental changes in a single variable. With all those things said, that's the summary of integration for our course, particularly in Module 5. As always, stay in touch if you have any questions or concerns.